In today's lesson, we are going to learn about exponential growth and decay. We're basically just going to learn some exponential formulas and apply them to some real-world application. Okay, so before we start with some of the formulas, I want to review a concept called the natural base. And natural base is when we have exponential function with base e. So, do we remember what e is? Well, e is if you look at this graph, and it's what does the graph approach as x approaches infinity. And what it does is it approaches an irrational number that is, I'm going to have to round this, so 2.718281828, and this goes on and on forever. So this is a famous irrational number. It was discovered by Leonard Euler, and it is actually used, it seems like a weird, strange number, but it is used most common when we're doing the application of exponential functions. Okay, our first formula does not have base e, but our next one will. So compound interest, here's is a formula to write down. So I have a equals p parentheses 1 plus r over n to the power of n times t. Okay, so we have to know what each of these variables represent. So a is, so we're dealing with money. A is your end balance after t time in years. Okay, P is your principal. That's how much money you're starting with. R is going to be your interest rate, and that's annual interest rate. And then N is the number of times it's compounded a year. So is it compounded one time a year? Or is it monthly, 12 times a year? Daily, 365 times a year? Quarterly, 4 times a year? So things like that. That is your N. Okay, so we are going to calculate the scenario. If we invest a principal of $300 with an annual interest rate of 6%, and we're going to leave it in for 20 years and not touch this money and just see how it grows. And then we're going to look at 3 scenarios when it's compounded semi-annually, monthly, and daily. So all of our variables, I've got P, R, you have to write it as a decimal, time, T is 20, and then depending on how it's compounded, here are my N values, and now we just have to plug everything in to the formula to find A. So we just plug everything into the formula, put it in your calculator, and you should get that you will have, at the end of 20 years, it will grow to $978.61. Okay, the next scenario is just it's compounded more often during the year. So it's like that percentage is calculated 12 times during the year. So all I'm doing is changing my 2 to my 12. And when you plug that in, you will get that the money would grow to $993.06. So as you can see, as it's compounded more often, you end up with a little bit more money. So now if we're compounding it daily, that's 365 times during the year, you will get $995.94. So it's not a huge increase, but it is an increase as you go. And now we are looking at continuous compound interest. So instead of like monthly and daily, quarterly, it is compounded continuously. And here's where the natural base comes in. A equals, and then we call this part. It's the principal base E to the power of R times T. So same thing, A is the balance, R is the interest rate, T is time in years, but the E, just remember that is the irrational number that's about 2.7. And that is just a button on your calculator. Okay, so we're going to do the same scenario, investing $300, 6% interest rate for 20 years, but with a continuous compound interest. So A equals, the principal is 300 times E to the power of 0.06 times 20. So when you plug that in, you will get about $996.04. So there's your most amount of money that you can get. Not a ton more, but it is more. And then because we're dealing with an exponential function, I mean, the higher your principal is, or the longer you leave it in, this will grow more and more and more. Okay, so now we're going to look at something very similar, exponential growth or decay, but instead of looking at investing money and compounded certain amount of times in the year, it's just like a population exponential growth or exponential decay. Okay, so for this formula, it's very similar. We've got N instead of our A and our P, but we still have R and T. So this is still rate and time. And then the N's, this is just your final amount and then your initial amount. And then another thing to note is you have to know if you're dealing with growth or decay because you are going to change this R value based on that. So if it's growth, you're going to keep your percentage positive. If it's decay, you're going to make your percentage negative. Okay, so we're going to look at two scenarios. One, a population that is growing. So it starts with 110 million. It's growing at 1.42% annually, and this is going on for 10 years. So how much is the population in 10 years? So just plug in your numbers, your initial amount, and then 1 plus your percent as a decimal to the power of 10. So you just plug that in your calculator, and you will get that the population at the end of 10 years is about 126,656,869 people. And then another scenario for decay. So let's say a population is decreasing. It starts with the 12,426. It's decreasing by 6% annually, and this is going on for 10 years. So I have my initial amount. So this time my rate is negative. So 1 plus a negative is the same as just 1 minus. So when you plug that in for 10 years, you will get about 6,690, I'm going to round up, 3 people. Okay, so then the next part, we've got the continuous instead of annual. This is the continuous, so we have to deal with that natural base again. So this is N equals our initial amount times E to the power of K times T. I'm not entirely sure why we switched the R to a K, because it's still your interest, it's your rate, but because it's a continuous growth rate, we just change the letter instead of an annual growth rate. Similar though, if we're dealing with exponential growth, we want our K value to be positive, but if you're decay, we want our K value to be negative. Okay, so same scenarios, but just using this formula instead with the the continuous growth and decay. So it's just a quick plug it into your formula, put it in your calculator, and that's it. So just notice how, because this was the decay one, that my rate, the K value, is negative. So when you plug these in your calculator, you should get this one, the growth is about 126,783,431. So a higher increase than our last example. And then the next one, you should get, it should decay to about 6,820 people. So there is your full video on exponential growth and decay and compound interest. So good luck with your lesson.